We have one final talk for today's student workshop, and that will be given by Odile de la Beaujardière from the Air Force Research Lab, and she will be talking about modeling and forecasting the equatorial ionospheric density and scintillation.
So apparently you guys have already seen everything there is to see about the equator, so that's pretty good. You can go home now. And thank God I wasn't here all day, so I don't know what you've seen and what you haven't seen. But my talk is about the scene of starlight, and so do you have a pointer or something?
Yes, it is.
Oh, that's a pointer. So number one, I want to say that I want to thank all my co-authors. Number two, there was a meeting about the scene of results that was, some of you went there, and we had 3 full days from 8 in the morning to 6 at night about some results. So there's no way I can talk about all this, so I'm not going to talk about most of the stuff we saw with CNOV, but just some of the stuff that we have. There is also articles that have come out. We have a special issue of GRL on the CNOV satellite results, and we are looking at another special issue. So what I'll talk about, an introduction, but you already know all this, so I'll go very fast. So what do we do about those scintillation and electron density profile we want to understand? The answer, of course, is the scene of mission. There is no other answer than the scene of mission. I'm just kidding, because there are lots of other answers. And then we will then show some new results from CNOV. And I'll try, as I was showing them, you know, the major questions we need to answer. Because we've been flying this satellite for 2 years, but there is so much we don't know, it's just unbelievable. So unfortunately, things are not as easy as we thought they were. We launched our satellites in 2008. And I'll just so briefly do an introduction that will go very fast. And as you know, you have a fountain effect like here in the equator. And I think you already went understanding the fountain effect with the maximum ionization around plus or minus 15 degrees from either side of the equator. So you know that. And this map was already shown earlier. I've seen that was flattened out. This is the map showing the 2 bands of the irregularities. It's taken by the GUVI satellite on time, and it's the image most seen from all of the NASA satellites, actually. That's the most famous image, is this one. It was taken during active times, and you have to realize that all of these images, they really cheated in doing this, putting that together, because every single of these images is at the same local time. So it took a long time. It took 24 hours to do it, but each of the image is at the same local time, which is, I don't know, in the early evening hours. And then you see the bands of increased ionization, and within these bands you have all those plasma depletions that we've talked about. These black streaks here. And that the plasma is non-stable. We've already seen that also this morning several times. And you see the point that, and it was also shown here, what counts is the fact that the E region down at the bottom of the field lines is a perfect conductor during the day, so you have much less irregularities during the day than during the night. And indeed, you have those, when both of them go into darkness at the same time, might be a time when you have a maximum of scintillation. And then we went through the Rayleigh-Tailor instability also. I think there were, even me, I saw several slides on it. It's really great because it's a feedback, it's a positive feedback mechanism. Once you start putting in this gradient, you have a horizontal gradient. If you start putting a wave or disturbing this gradient, then the polarization electric field is such that it accelerates, it increases those irregularities. And it's the equivalent of a light fluid being under a heavy fluid. And then the light fluid needs to go up, but it doesn't go up in a regular way. It goes up with those very irregular motions there. And that's what creates those scintillation, those irregularities in the ionosphere. And actually, many people, we talked about what triggers these, what is the thing that is going to start this irregularity. Several people had said, nah, the irregularities are always there. That's not the problem. The problem is, why don't they all of them grow? Because I think there are many opportunities for those irregularities to grow. And if I have time, I'll show you a small movie done from one of our programs by Eugene Su about this. The growth rate of the irregularity, this is the simplified growth rate, and this is the one simple way of knowing whether you would have irregularities or not. So you need to have the circumstances such that this gamma here shouldn't take too long. But this gamma is still, 1 over 10 minutes, about 20 minutes. So it's not, microseconds. It's a long time for those irregularities to grow. And it depends on the conductances, of course, in the E and F region. It depends on the electric field and their direction, the neutral wind, the gravity. And then it depends, of course, on the gradient, the vertical gradients in the ionosphere. That's one of the important factors. But you can see that we have this thing, and we launched this satellite in order to understand irregularities. But we launched it too high, exactly like Dave Heisel was saying. The place where we need to launch a satellite would be at 110 kilometers, up to 150 kilometers. But satellites have the bad habit of coming down to Earth very, very fast if we put them at these very low altitudes. So we still, I think that one of our problems is that we still don't know very well what numbers to put in all those growth rates there. And we still have to rely on models. But nevertheless, we do measure the electric field. We don't measure this. We hoped to measure the neutral wind. So we said, let's go for it. This was a little ambitious. So again, this was also mentioned. It's a seasonal effect. The pre-reversal enhancement is the enhancement in this plot shown from a model from Bella Fayer that occurs as it shows the vertical drift as a function of local time. And during the day, it's positive. Then it goes negative during the night. And just at the time it changes sign, it has a little hiccup there. It's called the pre-reversal enhancement. And this pre-reversal enhancement is due to the gradient between day and night in the E region. And so you can say that in order to forecast the time when you would have irregularity, a simple way would be, okay, let's measure this value of this pre-reversal enhancement. And this will tell us when and how strong the irregularities would be. This is fine, except that, as I will show later, with the CNOV satellite, this pre-reversal enhancement, we almost never saw it, especially in the beginning when it was the lowest of the solar activity. So that wasn't sufficient as a cause to predict the scintillation. And so one of the questions we have to ask ourselves is the strength of this pre-reversal enhancement the only cause of those nighttime irregularities? And I think the answer is no. And we still don't know exactly how to predict this amplitude of this pre-reversal enhancement between the wind, the conductivities, and the electric field. And even if you say, well, I measured that electric field, that's why I have a pre-reversal enhancement, you can put your values there. But why did you have that electric field at this place? So which parameters are the ones that control this pre-reversal enhancement? But you know, initially we had thought, well, it's enough to measure it there, so we'll know whether we'll have irregularities or not. And then this is one of the most beautiful figures, I think, that exists in our field. If we could see those irregularities, it would be the most beautiful spectacle to look at. This is taken in Jicamarca. It's an old image. This is the coherent echoes as a function of local time. We start here at 2000 local time. You have strong echoes in the Julia mode of the radar. And then, oops, you have those flames going up beautifully. And this is the kind of large-scale irregularity that, you know, would give rise to scintillation. And they cause, of course, strong backscatter from the radars. Those bubbles are spectacular. They rise extremely rapidly. And as you can, well, it's not written here, but at times they reach all the way to 2,000 kilometers altitude. And this, again, is Scintillation 101, where you show that's what we show to the colonels and the generals in the military. We show this slide, and it doesn't get more complicated than this for them. That the ionosphere reflects, refracts, diffracts, and this is a scintillated signal from GPS as a function of time, and you can see that you can have at times enormous perturbations, and it's problems of scintillation that really the Air Force used to have the money to fly the scene of satellite, because the military realized it was a real problem in their communication from Earth to a satellite through the ionosphere. And in here, you have a slide of a simulation of how those equatorial plasma bubbles grow. And this is a cut in the east-west direction of a program. And I'll go a little more, show some other images from this program called PBMOD. And again, this is one of the plots that explains the geometry that we use on the ground-based CEDAR station. They're called CEDAR for Scintillation Network Decision Aid. And it's a system of several stations in the world. And we just look at geosynchronous satellites, and we have several around the Earth of those geosynchronous satellites. And then with these fixed ground receivers, we measure the signal. And sometimes you have strong scintillation, and it's in here, it's only like severe, moderate, and weak. And one of the purposes of the scene of satellite is, of course, to do science, but it's also to try to have in real time a prediction of the times when you would have severe, moderate, or weak scintillation. So sometimes you can see you have severe scintillation just at the ends of the Appleton anomaly, and it's much less scintillation just in the middle here of this geometry thing. And communication is not possible when those large irregularities are present in the ionosphere between the receiver and the transmitter. You know that. And why do we care about scintillation? I've said that. And in here, scintillation, the plot I showed before was mostly at a lower frequency than the GPS frequency is. And a plot like this one is for UHF scintillation. It's not for L-band scintillation. And a plot of this, of the map, and showing, you can see the red and the yellow here. Red means if you try right now to look at a given satellite, to transmit through the ionosphere to a given satellite in geosynchronous orbit, you wouldn't be able to do it. And we actually produce maps like this on real time and try and also predict them ahead of time for those scintillation. So this satellite flies here in the ionosphere, and we measure the parameters, which are the drivers for the scintillation, or we measure some of the parameters that are the drivers for the scintillation. And it it is to have a continuous global scintillation forecast for communication. It also, a secondary purpose of the satellite is to also provide electron density profiles. So on the 3D volume, we want to provide electron density profiles in the ionosphere. The scene of goals, then, to drive this, I've said that. And interestingly, the military, once we tell them, you know, maybe we can go to 4 hours, maybe 6 hours, they say, oh, by the way, we need a 3-day. So 3 days in advance, there is a real need of forecasting what the ionosphere is going to tell you in 3 days. And actually, that is really something we need to work on as a community, because it's not only an Air Force need, it's also a NOAA need to understand what's going on long in advance. And for this, you need to understand if the sun is going to have any problem and how those problems for the sun, the coronal holes, are going to propagate to Earth. Are they going to hit us? If they hit us, what's going to be the effect, and so on. So it's a really complicated problem, and I think a community as a whole, that's what really unites us. This solar wind, magnetosphere, and ionosphere community is united because of this goal to try to understand and to forecast over a longer time period what happens. So right now, frankly, we don't really know even how to nowcast what is going on. So we are far from being good at forecasting, but we have to learn. So this satellite is an inclination of only 13 degrees, and we do not have fuel on board the satellite. So this is the reason why our orbit is 400 perigee and 800, a little over 800 apogee here. So it's about an hour and a half orbital period, and we have data in real time thanks to NASA from a TDRS transmitter. We were launched in April 2008 from a Pegasus, and in addition, within the mission, we have a ground-based component of those scintillation beacon receivers and several other ground-based instruments. And those are the instruments that we have on board. So we have 6 instruments on them. We have a GPS occultation receiver. It's called CORIS. Paul Strauss from Aerospace is the PI. And it measures line of sight total electron content. It's kind of neat because as with your GPS from the satellite itself, from the scene of satellite, we look through the GPS satellites going there, and we see them going through the ionosphere itself. So it crosses an awful lot of ionosphere, that line of sight. So even on times of very small scintillation, because it integrates it, then we do measure a scintillation. So kind of, I didn't realize that before we launched CNOV, but it's a really nice way of measuring the presence of scintillation in the L-band of irregularities, if you want, meter-scale irregularities, even when the scintillation itself between the ground and the GPS satellite would be fairly small. So we also have an electric field instrument with those booms, enormous booms here on either side, done from NASA. Rob Pfaff is the PI, and it measures the electric field vector, the 3 dimensions. It measures the magnetic field, 3 dimensions, and it also includes a lightning detector. Then we have an RF beacon. This is Paul Bernhardt from NRL who did this. So from the satellite, you send in 3 wavelengths, all coherent, VHF, UHF, and L-band, and from those, you calculate whether you have scintillation or not. You can also do tomography to then get the electron density profile. Then we have a planar Langmuir probe. This is an AFRL instrument. Now it's Patrick Ruddy, I should have changed that name, is the PI. And we measure from it the ion density. And most importantly, we measure the small variations in ion density, and we measure the electron temperature. And then we have 2 ways. That's the second way to calculate the velocity vector. We calculate it from VFI. We also calculate it with the ion velocity meter University of Texas at Dallas. Rod Hillis is the PI. And we measure not only the vector ion velocity, but the ion density again, and the ion temperature. So on purpose, we have 2 or 3 measurements of the ion density from this instrument, and this instrument. Of course, when we turned on the satellite, those were 3 completely different numbers. So we had to reconcile those 3 numbers to get the same value. And we measure the temperature of the electrons and of the ions. And then finally, we have the neutral wind meter developed at the university, UTD again, by Greg Earl is the PI, to measure the neutral wind velocity. So it has quite a lot of instruments on it. And this is the map of the CEDAR ground stations. And the data from those, you can see there are quite a lot. And Keith Groves from our lab goes everywhere in the world to put those ground stations. So all the young people want to go and work for him because he has those trips in those beautiful islands in the Pacific to install the things. And then they don't realize that sometimes the poor guys, they get stuck for 2 weeks in the beautiful island, and it makes it a little long, because they're in a tent and it rains, and it's not always as funny as they thought it would be. And it's a lot of work, too. They work day and night to put all these stations. But it's absolutely wonderful how in a few years he has been putting stations, continuing to put stations everywhere. And in particular in Africa, it's a big effort we are doing now to put those stations in Africa here. Because as it turns out, it's above Africa that we have the most intense scintillation, by far, actually. Africa is the king of scintillation. And that's another question. I'm not quite sure why Africa has so much scintillation. So in order to do this forecasting, we have several ways, but most of what I want to talk about is based on a program that does the forecasting. It's called PBMOD, and John Rayleigh is the one who developed this program. So to forecast, first we need to forecast the ambient ionosphere, and then eventually we'll need to forecast the scintillation. So we calculate the electric field, and it's not easy because the satellite is only at one place, and even if it were to give us the right value, we still would need to obtain the value, at this T everywhere around the world. And also, whatever we see, the ionosphere that we see is a function of the ionosphere that was there before. So usually, in order to calculate what electron density profile is happening just at this very minute, in our models, we need to know what has happened. And usually we try even 3 days before to start the program and to get it, because the ionosphere density we see today depends on what was there several days before. So we calculate the electric field everywhere from the in situ data. We calculate the other drivers. And right now, as it turns out, we do not have yet a neutral wind driver, because even at 400 kilometers, the neutral density is so small that Greg Earl and his people have not yet calculated neutral winds out of it. So the driver, the electric field, is the only driver we have so far. And so we have to assume a model. So for whatever quantity we don't know, thank God there are models, and that's what we use. From there, we derive this linear growth rate. And from this linear growth, and this plot here shows one of the output of the PBMOD. And the red, so in his local time and altitude, and this is for a whole day, so this would be the pre-reversal enhancement raising the ionosphere up. And this black line here is the value of the pre-reversal enhancement. And for the regions where that's not the region, it's the regions where the growth rate. So we put in a map of the growth rate. And the regions where the growth rate is big enough, then we start the second program that comes in and calculates then the nonlinear plasma irregularity evolution and how they change. And from there, the program calculates a spectral index. And it's kind of unbelievable because we want to know the scintillation with, meter-scale irregularities, but the program is really a 10-kilometer, 100-kilometer program. So we assume that the spectrum of irregularity is going to be a beautiful power load, just going down very regularly. And by looking at the large-scale irregularities, we deduce the value of how many of the small-scale irregularities they are. So in other words, if you open the hood of the programs that we use, you realize that you have an awful lot of assumptions that were done to arrive at the value. And of course, sometimes we do have values, so there is some part that is not entirely finished, is this part reconcile model and observations. What we see with the model, and it doesn't always work. And we produce maps of scintillation. And this is an example of a calculation of the electron density profile at 0,1 UT. It must be above Hicamarca. Latitude is here. Yeah, you can see this is above Hicamarca. This is the equator here. And you can see the beautiful Appleton anomaly. And actually, this model of PBMOD gives, in my opinion, is one of the best, if not the best model to predict, to calculate the electron density profiles everywhere. Because we've done a lot of validation of this model. And compared to other models, it gives extremely good values. And we even compared it to the game model, for example, assimilating all of the TEC measurements that you can have hundreds and hundreds of TEC measurements. And for some of the parameters, actually, PBMOD was doing better than those other models. And from there, we do this 3D electron density profile, and then again, we calculate the irregularities. So again, on this PBMOD, this is a snapshot of a few hours, I think. We start in local time 1900, and this is 21.5. And this is a snapshot of how the ionosphere varies in this smaller model that calculates scintillation. So the first thing here, you can see these very small little green things coming up here. So the irregularities are there, and then they grow, and some of them make those beautiful trees going like this. And this time you can see 1,000 kilometers altitude is up here. So they can grow, and they can grow extremely high. And an interesting point for you to note is that if you are above one of those irregularities, whether you look at this one or this one, so if you fly with a satellite right at this altitude, you would be above one of these equatorial plasma bubbles, but you are not going to see a decrease in your in situ density. You are going to see a little maximum in your density. It's because as the plasma moves up, as the velocity inside these equatorial plasma bubbles pushes the ionization up, and you see an increase in the local density rather than a decrease in the density. So this could be a precursor, if you want, of a density between you. So I plot this because this is one of the plots from John Rader, and he asked a question, but the given plasma drifts, PBMOD can explain the observations, but the real question is, why do drifts occur at the time they do? And I think if we understand better the electric fields themselves and what they are, we would be much better off. So now I'll talk about some of the results that we had. And one of the items I want to talk about is some of the observations during at sunrise rather than at sunset. So the nice thing about CNOF, even though it was a disappointment to fly during solar min, one of the nice things is that it was really during the lowest of the solar winds we had ever seen. So it allowed us to see some phenomena that we didn't know really existed, because they were kind of maybe masked by other phenomena. The pre-vessel enhancement in the upward drift is rarely seen. That's one of the results we've seen. And at the altitude of our satellite, which is at 400 kilometers and above, especially in the beginning, it's only starting in the month of March or April that we started to see strong irregularities at our altitude at sunset, because in the beginning, for most of those 2 years, most of the plasma irregularities were observed after midnight. And then they were also seen deep plasma minima at dawn. And on those, I will show some of them are caused by upward plasma drifts, and others are seen by downward drifts. And these downward drifts, the drift is minimum, or it's the maximum downward, if you want, around 05 or 06 local time. What we also have seen is the tidal effects are predominant in many, many cases during the solar min. And I don't think we have yet unscrambled all the effect of the tides. So that's another point where I think a lot of effort needs to be done, is understanding the tidal effects. And what also was our surprise is even very small changes in solar wind parameters and in the DST index have profound effect in the nighttime ionosphere, much more than we saw, because before that we had studied all the big magnetic storm, you know, the Bastille storm, and all the other storms that happened during solar max. But then during those mini storms that don't even qualify as storms, we still had a profound effect in our data. So these are some of the results that we saw. So I want a few slides on those depletions that occur at dawn. And I call that the depletion. And sometimes when I say that, some of the purists say this cannot be a depletion because an equatorial depletion has to be no more than a kilometer wide and so on. What I mean by this word depletion is when I fly with my satellite, I see a minimum and a deep minimum in the in situ electron density. So this is an example of those. And in this plot, we have the electron density on this side here and the altitude of the satellite on that side here. The satellite here, this is just one orbit here of the satellite. The satellite starts here. It crosses the equator at this point, goes down to 400 kilometers and goes back up to 800 kilometers. And then the in situ density is this green line, is this black line here, whereas the green line is the density at 1 second data, and the black line is the 1 minute density data. And in here we do the Fourier transform of the changes in the electron density. And as you can see, this is in June, and it was programmed so as to stop at 3 o'clock in the morning, because everyone knows that there is nothing happening after 3 o'clock in the morning. And then we look at our data, and the only interesting thing happening is after midnight, and certainly it's more at 4, 5, 6 o'clock in the morning than before that. So we changed our stuff, and now we are programmed to continue calculating that Fourier transform later on. But before that, we didn't even calculate those very high, highly changing densities here. And in this other display here, in addition to, of course, longitude, latitude, time, UT, etc., we show the map. And the green line here represents the equator, and the red indicates the satellite. And when there is a heavy line here, it indicates the time when the satellite is in darkness. So one of the complications we found in understanding this data is that we are changing everything at the same time as we go around an orbit. We change the longitude, we change the UT, and of course we change the altitude too. So it's difficult to understand exactly what's going on because so many of the items is changing. And as it turns out, I might give you the good news now. The good news is that even though our satellite didn't do really as well as we wanted to do, and even though we are not as good as we should be to predict electron density profile and to predict scintillation, we still are planning a follow-on to that satellite. So there will be a follow-on, which will be a more simple satellite probably, and we are hoping to be launching in 2015. Now, whether our satellite will still be alive in 2015, I don't know. It depends on satellite drag, because at 400 kilometers, if the sun starts increasing, the neutral density will increase, and we will re-enter before. So the next satellite will have propulsion on board, and our aim is to keep at always the same altitude. And we would be at an altitude which is low enough so that the IVM data can consistently provide the vector electric field. And hopefully we would be able to change a little bit the altitude if the F region changes because of the changes in the solar wind. So anyway, let's go back here. What we see here is one of those plasma depletion here that occurs at dawn in the morning, and the local time in here, I forgot what it is, it's close to 5 o'clock. The CNOV flies here, and these are two terminators, the terminator on the ground, terminator at high altitude, and this point here is the terminator in the E region. So it's usually when the satellite is above the E region terminator that we see those very narrow and very deep decreases in the in situ density. And now I'm blowing up. This is exactly the same plot I showed before, and simply blown up. You can see here we go down very steep decrease, and then it comes back up more slowly, and the E region terminator would be at this location here. And on this part here, for exactly the same time from this satellite, we measured the upward drift from the VFI instrument. And you can see that actually irregularities in the electric field are seen before you see the deep downward depletion. And that has been found before by the previous satellite or rocket measurements here. You can see that the upward drift went all the way up to 200 meters per second. And in here, when you go down, this very steep decrease here corresponds to an increase. So that wall here is where the upward drift is maximum. And inside those depletions is when you have high upward velocities here. And then as the, this is the sun is completely shining here, and then the upward plasma drift becomes much smaller. And we could have a bias in this value of this drift here. Now, we took the values of this of the plasma drift, and we put that in the PB-MUD model. And we model this, and we can see that with those drift, we have the model this is one of the snapshots of the electron density profile as a function of altitude here. And the red line here shows a small E region, and it comes, and you can see here, we came with CNOV, and we measured the in situ density. And on this particular day, at least, it shows that the model PB-MUD was giving a value exactly the same as what we had measured in situ here. So we have some confidence here. And what happened during this event then is that really the maximum density is here. This is FOF2. This is the height. I mean, it's the height of the F region maximum. It's at 1,000 kilometers. So we are at dawn. It is 5 o'clock in the morning. The ionosphere is totally blown up. It's above us. And the peak, the F region peak, is actually at 1,000 kilometers. It's way above us on this particular day. And we see that over and over again during those months of June, a little bit in July, although on that year we didn't have many July data. So this is one of the types of plasma depletions, and it's due to this upward moving electric field. And this is another snapshot of the value of PB mod. And we've ran PB mod two ways, and those are the two results. And this is a snapshot as one UT. Now we are looking at this one UT at all the longitudes around the Earth here. And the lower part is what would it happen if you take simply the Bella-Feyer model, the Feyer and Shirley's model, to calculate the electric field. So this is what you expect. You would have a density here. This is during the day, the F region. F region peak is about 300 or a little lower here. That's the nighttime. That's why it's blue. You know, there is nothing, very little ionosphere down here. And so this would be the expected thing if you take the model as an input into the PB mod model. And this is the value. If you feed it the values we measured in VFI, you see large differences. And you can see that you have other times when you have, times when you have of those depletions or lower density if you fly here at the same altitude. You can see the F region peak is much higher. And you can see the F region peak is those black lines here going up and going all the way to this altitude here. And then the day arrives and the sun fills it in here. And now in here, we are cutting it. Instead of cutting it in the east-west direction, we cut our ionosphere as a function of latitude here. And again, you have the CLIMO model. So it's run with the climatology value of the electric field. And you do have the anomaly, the two peaks of the anomaly in that local time here. And that's what you would expect if you take this Bella-Feyer shearless value for the NMF2. But instead, when you calculate with the electric field that were measured, you can see that the anomaly went to much, much further north values. And then the density on one side is smaller, on the other side is bigger. I don't know why we have a little maximum here. So it's a profound difference between them. Another example here, this is in September. We see another of those decreases. This time it's at 670 kilometers. So those events are not only seen at 400 kilometers. We see them at all altitudes. We see them even when the satellite is at 800 kilometers. And the reason I selected this one is that we had a CHAMP satellite here coming in. And this, I measured the width here. It's only 14 degrees in the east-west direction, this minimum that we see in the density here. And now you can see we adjusted taking plasma samples at higher frequency later on during the day, and you can see on this very quiet day, it's the only place where you actually see irregularities. It's only through here, only at this dawn local time here. And the reason I selected here is that we have a CHAMP satellite that is flowing north-south at the same, within a few minutes of where CNOVS was. So CNOVS was coming this way, the CHAMP satellite was going north-south. And it measured also a depletion here, and that's the red value in this plot. So in here, we actually have much more than one orbit. This is the equator, this is one pole, this is the other pole, and these are the other equator crossings on the other side, on the evening side. So you can see the anomaly here. And the CHAMP satellite here was at 350 kilometers. It sees that the in situ density going down very deeply here. The green line is what to expect. The green line is the IRI model. You see the huge difference between the IRI and the actual density. And when you look at the width here of this effect, you get 50 degrees. So you have the whole ionosphere that's depressed, that is much lower, around 50 degrees here in this thing. So those are biggies. Now, this is from, I will show later on the DMSP paths that corresponded to this time period. Now I want to show another example. What am I doing here? Now I want to show another example. And this is maybe more often that we see this. Those are other depletions, and I call it depletion again. It doesn't mean it's like an equatorial plasma bubble. It's simply as we go with the CNOV satellite here, as if along a time and longitude, we see the density decreasing, having a minimum. And our minimum here was at 05 local time, and then recuperating and getting to higher values. And this is a much more regular V-shaped value. And the interesting thing is that we have several examples where it's an hour later, so at 5 o'clock is when the density is minimum, and it's at 6 o'clock that the upward velocity is minimum. So it's the maximum downward velocity. It reached almost 100 meters per second here at 6 o'clock. And in between in time, you have the minimum in the east-west direction, or really the maximum westward drift. So nice corresponding values here. And it's first the density goes down, and then the value of the downward drift is maximum at 6 o'clock here as we get there. And this is quite often that it happens. And actually, in many models, you also see that the value of the density, you also see in the models very often, in the average models, that the velocity is minimum or maximum westward just before sunrise here. And that causes the density also to decrease. And it could be simply, I'm not quite sure what it is because we haven't yet modeled this with the PB mod. So I don't know if it can be simply expressed in terms of the F region peak going down. And this is to show the model here. So this is one of the plots by Bella Fayer. And you can see average that models calculation here with the arrow bars. And then the line that he shows is the value of the model that he uses. So if you use the average model, you're actually in this black line. But if you look at the average values, you should see that it doesn't always match. But you can see that very often, this is March, April, and September, October. It's also shown in the statistics that that's the time when the velocity is the largest and downward here during the day, and it changes depending on the season. And interestingly, there was an article that came out just recently by Liu et al., and they calculate here the plasma drift, and these calculations are for 3 different longitudes here. And they show that this drift can be either upward at dawn, or it can be smaller and downward, or much deeper and downward, also at dawn, because this is 5 o'clock local time, all due to a mixture in his model of tides and planetary waves. So in other words, you can have many people doing many programs and many theories, and you can have many reasons to have those variabilities in the upward and downward drift. And I thought because of that, this was a very interesting article showing the variability that you can have depending on your longitude and on the season in the vertical drift. And now for the same first plot that I was showing you, we have here the value of the DMSP satellite. So the DMSP satellite, as you know, flies at 850 kilometers, and we have 3 DMSP alive right now. So it flies around 6 o'clock, 5:30, and 6:30 in the morning. And interestingly, most of the irregularities, as was shown before with the DMSP satellite, most of the irregularities we expected were the ones when that satellite crosses the 1800 or 1830, 1700 local time. And we kind of didn't look too much at what happened on those times in the morning. And oh my gosh, you know, because of CNOV, we realized that this is actually, during solar min, that's where the activity is. It's not at all at 6 p.m. It's at 6 a.m. So really, you guys are students. It's exactly like a graduate student. Most of the activity is at night. It's after midnight, you know, and during the day, nothing happens. So the solar min with CNOV is exactly like the activity of the students here that we saw. So what we saw for those depletions, those large decreases in the density, they are more frequent over Africa, America, and Asia. They have a seasonal dependence. And for example, in a day in September, it occurred 77% of our CNOV orbits. If you look in November, it only is occurring 15% of those events. Local time dependence, maximum around 5 a.m. They occur above the E region terminator. So this is the location where they are in local time. Latitudinal dependence, they are much wider in latitude than in longitude. And of course, they are seen not only in CHAMP, which is at 325 kilometers, but also at TMSP. So when you have an event like this, you realize that actually it's above 840 kilometers that the F peak should be. So it's one of those times when the whole ionosphere is lifted up. And someone showed this plot before. Oh man, semantic temper protection alert. Oh, I'm alerted. So this is an article by Louise Gentile, and there was a first one by Bill Burke. And those plots are plots taken from the DMSP data. And I was telling you, we look at DMSP, and we are really interested, and we realize how many times we have irregularities in this data set. So what we have here is longitude. This is the map. This is the longitude of 0 of London here. And this is not latitude. This is simply time, going January, et cetera, through December. And this is SoloMax, 1999 to 2002. So it's a mixture of several years' worth of data here. So at any longitude, you can see what the probability is to have irregularities of a given value here. And this is how you can read the irregularities, how many times you have irregularities. And you can see that it's longitudinal dependent at SoloMax. And you also see that kind of, sort of, it follows that black line as indicated before, which is the time when both feet on either side of the magnetic field line, you have sunset occurring at the same time. And there is a significant, then, a change depending on the season and, of course, the longitude here. So we did this for SoloMax. We did this from 94 to 97, which is the previous solar min. And this is what we found. So you still find those irregularities, and it looks like this, you know. And then we did it now. Zilch, nada. Nothing. We don't see them. So this plot becomes this plot when you get the solar min, which is the deepest solar min, because that was the previous solar min, and that's our solar min now. However, if you do exactly the same plot with exactly the same scale, and you look at 2008, which is also solar min, you realize that this is where the activity is. I was telling you, it's in the morning. It's exactly the same sunlight. This time we do this for the dawn side. And my golly, look at this. You see, it's between minus 60 and in here plus 60. And you do have 1, 2, 3, you know, knowing that people are looking for 3-wave patterns and 4 maxima, we look for them. And we kind of see them all the time. And maybe you have them here, 1, 2, 3, 4 of those wave patterns here from the tides coming in. That you can see the variability in June and July is when you have the most of it, but it's not the only time. At other seasons, they occur at other longitudes. And this work is not finished. We haven't done it for 2009 yet. And Eugene Dao is going to talk about this at his poster. He's going to talk about it tomorrow, so I'm not going to spend too much time. He's trying to do those averages of the times when you have irregularities, and he counted even very small irregularities in the PLP data, in the in situ density here, and you have local time going in, and then the day of the year again, and you can see that a lot of it is here. And you can see these maxima, but they are simply due to the changes in the orbit here of our satellite here, where in 30 days you come back to the same location of the perigee and apogee. And in this plot, you see the map, you see longitude here, and again, you can see the regions where you have most of the scintillation here, and you can see 1, 2, 3, 4, maybe the 4-wave pattern in the probability of scintillation. And this is done for a whole year average. And Eugene Dao already submitted this paper. Okay, so that was one of the findings with the CNOV satellite. Another finding is about the neutral atmosphere. What we found, changed it. Another finding is regarding the effect of the sun and co-rotating things coming to us. So this is work done mostly by Bill Burke and Louis Gentile at our place. And we have here the value on top. This is several days, this is several hours. UT is from 20 to 24. The red line here is the value of the density of the solar wind. So now we are looking at the effect of the solar wind, and does this solar activity have any effect down in the equator? So you have the solar wind here, and the velocity of the solar wind, the density of the solar wind varying and having a fairly steep increase here and staying on the plateau for quite a while here. And the blue line here is the velocity of the solar, the blue line is the velocity of the solar, The red line is the velocity of the solar wind, and the blue line is the density of the solar wind. And it's not marked here because early on the value was not available, but there was a peak. It was low down and a peak here and coming down. So this event was solar wind coming in and pushing with a large increase in the solar wind velocity. Almost at the same time, but a few hours after, as we come down and look at CNOV, during these few hours, CNOV has time to go twice around the Earth. So in here we have 2 orbits shown. The black line here represents the time when the satellite is in darkness, the nighttime passes. So the first nighttime pass, corresponding to this time, was, there were quite a lot of irregularities, but nothing to write home about. And the next time we pass, a few hours after, you can see very, very deep depletions, very, very large irregularities here. And a few hours after, it was 2 orbits after this, when you come in with the CNOV satellite and you measure the density, you can see an enormous ditch. Again, it's a time when the whole density is down to almost nothing, and I presume that most of the ionosphere has gone up to much, much higher altitudes here. So it's only 3 hours later that you see this almost total, quote, disappearance of the ionosphere because most of the plasma has moved above the CNOV's altitude. So these changes in the solar wind density are seen very fast in the equator when we look at these CNOV data, and with rapidly scintillation producing irregularities. And then when you get to this point here, you wouldn't see scintillation anymore because there is no density. The density has gone. So you're okay. You can communicate. 2 minutes? oops, 2 minutes, oops, I go too slowly. So I'll go to another aspect is regarding the neutral density, the neutral atmosphere. What we saw, and this is a work done by Cheryl Wang, and she has an article published on it, and she's also going to give a talk tomorrow about this. And she realized, she saw that during some times, the density was very low at some longitudes there. And this is true for both day and nighttime. And the value of the density seen in the DMSP also shows a broad minimum here in the electron density going north-south with DMSP and east-west with our own satellite. And interestingly, we see those decreases in the data of neutral density from the gray satellite here. And the gray satellite is shown here and shows a decrease in the density here. Okay, so I don't have time to talk more about this. I should go fast. Now, I wanted to go to a value of the 3D plume model that's done by John Rederer, but I guess you guys, you will have to read his 2 papers and showing his simulation. And, you know, how do you plot the output from a 3D model? It's almost impossible, so you have to cut it east-west and north-south, which he did here. And this is, if you are fixed in one location, Jicamarca, from his model output, one of those equatorial plasma bubbles would look like this, but what he plotted here is the spectral density of irregularities that are 20 kilometers long in size. So this is how many 20-kilometer blobs that you have per unit volume. And it's from there that he calculates the scintillation index, you know, looking at the spectrum of all this density. But it really looks like the very first of the big plumes that I showed before of Jicamarca. And again, this is one other times of validation of his 3D model, comparing it with scintillation from the ground. The blue is what the times when the model would show a lot of scintillation. And you can see that it corresponds fairly well, not only in the magnitude, but also the time of onset, which is important here. And now we go to another subject for Xiaosong Huang. And I think he might have forgot if he will show that plot. In here, what he's after is articles by email and then Park looking at an imager from a geosynchronous orbit. We're calculating the value of the drift of the equatorial plasma bubbles, and from there calculating the drift of the plasma. But actually, the drift of the average, the drift that you measure of those bubbles moving eastward or westward is larger at times from the average that you would calculate in the models. And what Xiaosong Huang has done is he's looked at it and he calculated what these drifts are and was explaining the difference between the average ambient drift and the drift of motion of the bubbles. And in here, he shows two of those large regions of density, and you have two here. You have this is another event. And look at in here, he plots the east-west velocity during those times of depletions in the density, which is shown here. The upward drift is shown here. All this is VFI data, and this is PLP data. And you have here, interestingly, some of those, a lot of them have a westward moving, large westward drift inside those bubbles. But other times, you have eastward, and on this particular time, it goes east, then west, then east again, then west. So several things as we cross with the satellite here. And he explained it, is what I called his Y paper. So you can see this Y letter here. And he calculated that you have in here charges on either side of the depletion, which induce this electric field from those space charges in this direction. And change it to the two upward and eastward velocities, and from you have it here in one direction when the depletion is in this direction here. When the depletion is the other side of that y, that electric field is downward. So you can see that if you translate those two electric field vectors into velocity vectors, you realize that in both cases you have an upward velocity, but you have at some times a westward velocity, like here, and other times an eastward velocity. So that's why he explained within those narrow plasma bubbles the value of the velocity inside the bubble in the east-west direction. And this y here, so when you have the velocity going east, west, west, it's because we are crossing really two different parts of this thing. And interestingly, the actual models show exactly the same thing. This is the model from John Rederer of the plasma bubbles, and within it, he calculates not only the up and down velocity, like in this plot. This is an east-west cut of his plasma bubble, and it's up very large, higher than 100 meters per second. The east-west direction shows exactly the same thing. When you have a bubble inclined in this direction, then you have a westward velocity in it, shown here, and when it's inclined in the other direction, we have an eastward velocity. So this was a very kind of a clever paper that he has done. So I will not continue here. I don't have time to do this. I don't have time to do this. I'll just go to summary. Am I allowed to get my summary? Oh.
Real quick.
Real quick. We launched to study the forecast. We had done depletion. Some of them are due to upward plasma drifts, other downward plasma drifts. We see them at all the altitudes. They are often associated with irregularities. There's strong dependence of them in latitude and longitudes. We see them with the other north-south satellites, and the PB-MOT reproduces them very well. Number 2 set of summaries. The PB-MOT can explain the observations fairly well. You have broad reductions in neutron and ion densities, and please listen to the talk by Cheryl Huang in this meeting here. She's going to talk about it. The donor motion of the bubbles. I didn't have time, and that's it.